also the uh, sole distributor of Metrovid DMAs for North America. Metrovid DMAs series instruments are dynamic testing machines based on an innovative one-piece high-rigidity test frame concept. The one-piece test frame has been designed to offer the largest force, stiffness, and frequency analysis ranges available. Metrovid is dedicated to the accurate analysis of the viscoelastic properties of today's most advanced materials. And here's just a testimonial from one of their customers over in Spain, from Izidi Bergio. The Metrovid DMA Plus 300 machine allows us to directly measure the nonlinear dynamic mechanical properties of polymeric materials at high frequencies, which is not possible with the conventional DMA machines. In this way, we can go deeper into the research of the digitalization of polymeric materials, which I think has a good relationship to what we're talking about today, which is EV sound and vibration damping, designing dynamic mechanical analysis experiments to measure the damping performance of sandwich structures. I'm going to get into a little bit about DMA and NVH at the start. As I understand, there's people from both sectors, so they might not be familiar with each one. And then I'm going to get into two really interesting case studies that I found online. So since we're going to be talking about noise, vibrations, and DMA, I think the perfect spot to start off with is just describing what a vibrational wave is. Vibrations can be described as the repeated motion of an object back and forth. When we describe vibrations, we often think of two terms, amplitude and frequency. The amplitude is the intensity of the wave, as we can see here on the graph to the left, and the frequency, which is the inverse of the period being the amount of time it takes for the wave to return to its original spot. And in terms of sound, sound and noise are just the vibrations in the air that we hear. The loudness is associated with the amplitude, and the pitch of that sound wave is associated with the frequency. And sources of noise and vibration for EVs and internal combustion engines, there's a lot of them. I've just listed a few here, but the list could go on and on. This includes the powertrain, the engine, the motor, really anything turning in the machine to help propel you forward is most likely making noise and vibrations that you're going to experience. The tire and road interaction is another one. If you're ever driving in winter tires, you'll definitely notice that they're a lot louder than summer tires. And environmental noise, like the wind that blows against your car. That can affect your handling, but you can also hear that as you're driving. And a big issue too is that since EVs are quieter, which we would think would be a benefit for reducing noise and vibration, it actually has a negative effect because a lot of these sounds that we wouldn't hear, like wind or road noise, which were originally masked by the noisy combustion engine, are becoming more noticeable and presenting more challenges for car manufacturers. And the reason noise and vibration is such a challenge for manufacturers is because these have adverse effects. This can increase driver fatigue, which reduces awareness and increases the likelihood of you getting in an accident. It can reduce the driver's vibrational comfort or acoustic comfort. While that might seem like a small thing, that's often how we associate the value of a vehicle, is how it handles, how it sounds. So these are just some of the issues that that noise and vibration are presenting to manufacturers. So the way that they're addressing this issue is by measuring and modifying noise and vibration characteristics of a vehicle. This field of study is known as noise, vibration, and harshness, or for short, NVH. And what makes this even more complicated from having to deal with, besides dealing with EVs and the new noise sound profile, is that drivers don't experience the vibrations and noise from the source, it has to travel through a path. That could be a structural path, like the engine mounts or the chassis, the seat, the steering wheel, and then the driver receives it. So there's all these different pathways that are getting to the driver, which really muddies the water when you consider that um, it's hard to identify where um, this vibration is coming from, which makes it really difficult to identify and isolate. And this thought process was thought of by Dr. Saha from his work developing vehicle sound packages there. Um, so manufacturers are addressing this issue on all levels, whether that's improving technology to make motors quieter, make tires quieter, um, or addressing this issue in the path between the source of this noise and vibration, between the receiver, um, by introducing damping or isolating materials, as well as addressing this issue in the cabin where the receiver or the driver is by inputting white noise or other noises to help mask these noises that we can't address. Today, I'll be focusing on dampers, which dissipate the structural borne vibrations and sound into heat. Now, that this is a better approach or a worse approach. All these approaches have their own benefits, and listening to any of the experts in this field, it seems like the solution of addressing NVH kind of requires a little bit of requires addressing these issues on every level to remedy this. So I'm going to begin with introducing DMA and how it relates to damping, and then I'm going to go through some case studies. First one, going through the benefits of a Metrovid DMA and how you can use it to do direct high-frequency testing. And then I'll go through a second case study with this group that used the time-temperature superposition relation to create a very interactive, comprehensive model where they're able to predict the performance of a sandwich structure in terms of frequency and temperature. I'm really excited to show that one. It's a lot of information, but I think it really shows how powerful DMA can be used as a tool in this field. And then we'll finish off with some closing remarks and questions. So DMA, or dynamic mechanical analysis, applies an oscillatory deformation to a sample and measures the response. This can be done through applying a force or a displacement and measuring the other. If we plot these against time, the force and displacement signal, we'll notice, unlike elastic materials, that viscoelastic materials will have a slight lag between the force and displacement response. This is known as the loss angle and is due to the viscous part of a viscoelastic material. The tangent of this angle, tan delta, or also known as the loss factor, is commonly used to characterize damping. If we take the force and displacement amplitudes that are measured during a DMA experiment, we can use those to calculate the complex modulus, E prime, or E star, sorry, which is the viscoelastic material property that describes the overall resistance to this deformation. This complex modulus has a real component and an imaginary component, which can be separated by using the measured loss angle delta. So the real component is related to the component of the material that stores the energy and later releases it, like a spring. And the imaginary component, or the loss modulus, is the component that's dissipated into heat, kind of like a damper. And this is what we're more concerned with when we're talking about damping applications. And then the tangent delta is related to these two moduluses, as it is the ratio of the energy loss over the energy stored. So we can see how that has a clear relationship to damping. And the main benefit of a DMA when measuring damping is that we can measure damping as a function of force, stress, deformation, strain, temperature, frequency, time, and creep. And viscoelastic properties like damping are all highly dependent on these parameters, and DMA gives you the tools to accurately control them. And this allows you to characterize performance as a function of one of these or a combination of these parameters to exactly replicate the end use conditions or to create a comprehensive model as well for you. It's really tailored for how you want to use it. And before we get into the case studies, I just want to go through a couple classic DMA tests to kind of show what traditional results you can get with a DMA. So the temperature ramp test, this is the bread and butter when it comes to DMA, which consists of vibrating a material at a set amplitude and frequency while changing the temperature. A temperature ramp test allows you to characterize the thermal states, like the glassy state shown on the left here, where a material will be hard and brittle, and the rubbery state, where the material will start to act more viscous. Um, the transition temperature, like the glass transition temperature highlighted here, this is indicated by the peak in the tangent delta or loss factor. There are other ways to measure the glass transition temperature, um, I should mention, but this will be the way we'll be using it in this presentation. And then you can also identify the operating range as well. So with a temperature ramp test, you can see where the material properties are consistent and don't really change too much. And if that's what you're looking for in an application, you can identify that temperature operating range. Or for damping, you probably want to operate near the glass transition temperature. So you can use a temperature ramp test for that as well. And as we can see here from the plot on the left, where the material transitions from a glassy state at 40 degrees Celsius and transitions to a rubbery state near 180 degrees Celsius, that these viscoelastic properties are highly dependent on temperature. And what I'll say here, I'm kind of a culprit of this. I didn't state this, but you should always state the frequency used for a temperature test. For this one, it was 10 hertz. And if you look at most ASTM standards, they'll have a listed testing frequency for you to use. They'll state as well, if you don't use this testing frequency, please state. And the reason is that viscoelastic properties are also highly dependent on frequency as well. From this plot here, we can see this effect where a temperature ramp test was done from about 30 degrees up to 190 at a set temperature rate while exciting the material at 3 different frequencies. And what we can see here is that the machine recognized or was able to recognize differences in material performance under each condition, under each frequency. So we can see here that increasing the frequency will increase the glass transition temperature. I have them listed on the right here. I should note too that this increase in frequency or increase in glass transition temperature will be slightly different for each material, but this is a known phenomenon where if you're increasing your vibration frequency, you will be increasing your glass transition temperature, which is really important to consider for damping as well, where we're really focused on maximizing the damping for our application. And then just to look at some frequency dependency behavior without temperature, we can also do frequency sweeps. A frequency sweep consists of vibrating material at a set amplitude while incrementally changing the frequency. As we can see here on the left, that this rubber damper was highly dependent on frequency, peaking at about 20 hertz. And frequency dependency is higher when the material is near its glass transition temperature compared to its glassy state, where it'd be more consistent and there'd be less of a frequency effect. And this is because the material properties change drastically near the glass transition temperature. So any change in strain or frequency can have an adverse effect on your material properties. And just as a fun comparison between elastic and viscoelastic materials, on the left is a frequency sweep on a piece of aluminum, which was being bent using a DMA test. And we consider aluminum to be elastic, and these material properties kind of support that. The modulus is consistent from 1 hertz, well, about 1.5 hertz up to 70 hertz, with a minimal frequency effect and very low damping. I should note that all materials have a little bit of damping in them, but rubber and viscoelastic materials, composites too, all have a lot more damping compared to aluminum and other metals and elastic materials. And when we look at the right, for that same frequency range, we can see that the rubber was highly dependent on frequency and had a very large amount of damping. This was just the previous example, um, but zoomed in on the frequency range to be compared to the aluminum there. Now we've kind of introduced DMA and went through some classic examples, I want to go dive into these case studies here. So the first one is the improvement of structural vibration damping performance of SMCs through SMC TPE sandwich structures. This was done in Spain with Leertijker and the University of Basque Country. And the goal of this study was to improve the damping performance of a sheet molding compound, or SMC, by integrating it into a sandwich structure with a viscoelastic core. Due to their low cost and high weight stiffness ratio, SMCs are growing in popularity but have poor damping performance at room temperature. So this group was interested in seeing if they could improve the viscoelastic properties of the SMC by integrating a viscoelastic core with the hopes of using in vibration critical applications like EVs. So the sandwich structure was composed of a carbide thermoset based discontinuous fiber reinforced plastic, which they titled EP. That's the hard outer composite shell. It has a high stiffness and high TG, meaning it will be brittle and won't have much damping at room temperature. And the viscoelastic core was a VersaFlex thermoplastic elastomer, which they labeled TPE2. The 2 comes from staying consistent with previous reports that they worked on with these sandwich structures. And this thermoplastic elastomer has high damping, but poor performance in certain environments, especially when it is exposed to certain environments with oxygen. And the 2 different sandwich structures they considered was an enclosed sandwich structure and a free layer sandwich structure, which they labeled FL. And the DMA test they did with these sandwich structures was with a Metrovid DMA plus 300 with 3-point bending. And the goal was to evaluate the damping performance of these different configurations at various temperatures and frequencies. I just realized there's a spelling mistake there. And what they did was they did some temperature sweep tests and frequency sweeps. I won't get too much into the temperature sweeps since we already kind of covered them some, but they found that the sheet molding compound or composite EP had 114 degrees Celsius glass transition temperature, while the thermoplastic had a glass transition temperature at 23 degrees Celsius. And this is kind of what they suspected anyways. The TPE has very good damping capacity at room temperature. It makes sense that the glass transition temperature would be near this temperature as well, because this is where the tan delta or damping will be maximized. But I did want to spend a little bit of time talking about the frequency sweep tests that this group did. So they did frequency sweeps from 1 to 500 hertz with a dynamic displacement of 1 micrometer, and they measured the performance at various temperature stages, at room temperature, all the way up to 140 degrees Celsius. I won't go through all the temperature stages today, but I just did want to highlight a few. And I should note too that this group was able to measure the material properties of different configurations from 1 to 500 hertz because they were measuring the performance directly. They did not use the time temperature superposition, which I'll touch on in the next case study, but essentially they were able to measure the different layer configurations directly with the Metrovid's DMA's high frequency capabilities, which you're not able to do with TTS. And I'll explain that in the next case study there. So the frequency sweeps at room temperature showed that the viscoelastic layer decreased the storage modulus. There's another error there. And that the free layer or FL structures were highly dependent on the viscoelastic layer's thickness. They also saw too that the sandwich and free layer with a 1 millimeter thickness viscoelastic core had similar performance. When they looked at the damping, they saw that the viscoelastic layer increased the viscoelasticity of the structure, and that the free layer with 1 millimeter thick with a 1 millimeter thick core was the most viscoelastic, um, and that the free layer structures were highly dependent again on the viscoelastic layer's thickness, similar to the modulus. They also noticed too that the frequency effect was not the same for each configuration, which showed the importance of measuring directly the performance in terms of frequency. The group also, like I said, considered different temperature stages, and here's just some of them at 40 degrees Celsius, 60, and 80 degrees Celsius. And what they noticed is that the TPE2 was successful in increasing damping performance at room temperature all the way up to 60 degrees Celsius. Um, the free layer structures failed above 60 degrees, and this was something they suspected with the viscoelastic layer being susceptible to environmental conditions, showing that the sandwich structures had a clear advantage in higher temperatures. However, they noticed too that the damping properties decreased the further away they got from the thermoplastic uh, elastomers TG, which is expected as well, since the material will not have a high tan delta, therefore won't have a high damping factor. I don't have it included in these pictures, but I should note once the um, temperature stages approached the glass transition temperature of the composite sheet, the TG again began to increase, and the frequency effect became very apparent, and the performance became a lot more inconsistent, kind of limiting the sandwich structure's performance as well. I will note too that although the TG was listed near room temperature, the damping performance did not peak at 25 degrees Celsius. We can see at 40 and 60, there was still very good damping performance dependent on what configuration was used. So the next case study I want to consider is actually two papers. I was trying to figure out how to break this up, but I couldn't. I felt like it was a dishonor to the other paper this group did without including both of them. So I've kind of combined them into two here. So the first one we'll talk about is the experimental investigations on viscoelastic properties of a sheet memory polymer. And then what they did with this paper was they essentially set up really nice DMA experiments and were really thoughtful in setting it up and measuring the viscoelastic properties of a sandwich structure and using time temperature superposition and acknowledging the limitations of it. And then in their second paper, sandwich structures with tunable damping properties on the use of shape memory polymers or SMPs as viscoelastic cores. They took that data and created a really comprehensive model and validated that through modal analysis. So really tying this all together and putting a nice loop on it. So to introduce the first paper here, part one as I'm calling it, they used a shape memory polymer as a viscoelastic core in a sandwich structure. The group used DMA to develop a material model to predict performance at different temperatures and frequency. They didn't state what the shape memory polymer was. They did state the composition there, but they didn't provide too much information on it. But it had high damping and a TG, or glass transition temperature, near 50 degrees Celsius. And the outer plates were aluminum plates, which have a high stiffness and were glued together. Were glued to the shape memory polymer with a Scotch weld DP490 from 3M. What's different for this case study from the previous one, however, even though they're doing a sandwich structure, is the group is using the time temperature superposition method, or TTS, to measure the performance. And for those who are unfamiliar with this principle, it's essentially based on the notion that a material will behave the same under different combinations of temperature and deformation rates. In terms of DMA, that's frequency. And typically, a material that is slowly oscillating at cold temperatures will exhibit the same behavior as a material um, at room temperature, which is oscillating very fast with or high frequency. So what this allows you to do is it allows you to run frequency sweeps at a set of temperature stages, and then you're able to shift your data to model the performance of the material at high and cold temperatures. Um, this is extremely useful when you want to get up to like the megahertz range. Tire companies use this a lot. Um, Steel companies use this a lot too. There's a lot of different applications by just understanding what frequencies are at play here, but there are some limitations, and you should be careful when implementing this method. The material needs to be rheologically simple, homogeneous, and isotropic. So this is when we think of a sandwich structure, that's not the case. We have different layers, so our material is no longer isotropic and homogeneous. So this is the main reason why I wanted to focus on this paper, was because they addressed that and with their study. The samples also must be deformed in the linear region, so small strains must be applied. And then to apply the WLF region, it should be in the approximate temperature range near the glass transition temperature and 100 degrees above the glass transition temperature. So you're sort of limited in your temperature range as well. And then successful testing takes multiple temperature stages, and this can take upwards like +8 hours. So this isn't always the most feasible test to do for a big group that's testing a lot of materials and where time is a big constraint. So that's often another thing to consider if you're thinking of using this method. So the way this group addressed the issue of a homogeneous sample was that they just tested the properties separate from each other, which seems obvious, but is something people often overlook when running a DMA test. So they evaluated the damping performance of the viscoelastic core separately in tension with a DMA 50. The time to temperature superposition was ran from 0.1 hertz up to 180 hertz with a dynamic displacement of 1 micrometer, which was established to be in the linear range of deformation. And they conducted this from temperature from 0 degrees up to 90 degrees with 5 increments for the temperature stages. And a sample of 29 millimeters long, 6 millimeters wide, and 2.97 millimeters thick was used. And we'll talk about it in part 2 of this case study, but the group fit this data to an analytical model and used modal analysis to validate these results. So these are the type of results you'll see from a TTS experiment on the left here. So the x-axis is frequency, and each line or each curve is associated with the frequency sweep at a set temperature. And we can kind of see how these offset from each other and how you can kind of shift them. I will note certain points were omitted from the analysis. I'll assume that this was due to resonant behavior or not following the curve that a lot of the other, not following the ideal curve that a lot of these other points are following. And essentially what they were able to do, if we look at the arrow to the right here, is that they were able to model performance up to 1 megahertz. And this can be done by using equations or visually inspecting and shifting your data sets over one another until there's good overlay with each other. And what they're able to do, like I said, is measure up to 1 megahertz with a master curve with a reference temperature of 40 degrees, but you could shift this reference temperature as well to 20 degrees, 90 degrees, as long as it's within your temperature stages there. It says 30 degrees there was the minimum temperature, but I think that was just an error in the plot because they did temperature sweeps to 0 degrees Celsius. And then on the right here, a good check to always see if your TTS data checks out is to do a Cole-Cole plot where you plot the storage versus the loss modulus here. And you should get an arcing profile with each data point overlapping with each other as we see here. So I suspect the plots or the points on the right plot were ignored or omitted because they didn't follow this ideal profile. So that kind of concludes the DMA portion of that. Um, but what they were able to do with this viscoelastic data was they're able to show that the core was rheologically simple, so it followed the TTS method, so they could move forward with their modeling here. And then they fit this raw data um, to fit a model shown below, which has springs, a damper, and some quasi-static components marked with K and H. I won't get too much into that because I feel like that exceeds what we're talking about today, but I did want to at least highlight that. And the nice thing about this model is that it was a function of temperature and frequency. So they essentially have like a matrix now of the material performance where they can um, fit their model to the exact operating conditions needed. So what they did with this model is um, they kind of took this and put it into the part 2 here of this paper. Um, so like I said, that this model was temperature and frequency dependent. So what they're able to do now is model, for instance, on the left here, they modeled the performance of a temperature sweep if the material was being excited at 200 hertz. And what they could do essentially is determine the optimum temperature for maximum damping for a signal at 200 hertz. So if we consider something rotating at 200 hertz at around 75 degrees Celsius, that material would have maximum damping. However, most applications require damping performance across a frequency spectrum, not just a single frequency. So this is what I thought was really interesting and innovative what they did. They modeled the performance with temperature ramp tests from 100 hertz up to 10,000 hertz. And what they were able to do is, well, get this really nice looking curve, but they were able to identify at what temperature would you have the maximum damping to um, absorb all that vibration. So the model that they determined from the model that the optimum temperature was 82 degrees Celsius, marked by the arrow here, and that was because this is where tan delta was the highest for each curve. I should note that the glass transition test suggested that or said the TG was near 50 degrees Celsius, which is often used to predict damping performance, but it truly depends on what frequency you're considering here. So if your material is being vibrated at 1 hertz, yes, the ASTM standard for finding a glass transition temperature is probably the suitable manner for that. But really understanding how your material properties change with frequency as well is important for damping applications when we're usually trying to isolate specific frequencies. And for this case here was 100 hertz to 10,000 hertz. Now, they didn't just state that this was the optimum temperature, they proved it. So this is kind of where they went over and beyond. Um, so they made their sandwich structure with this viscoelastic material, which was sandwiched between 2 aluminum sheets, and they did modal analysis on it, where you basically apply a dynamic force to a material and measure or a sample and measure its response. This is huge in the car industry, automotive, really anything that's moving. Modal analysis is being done on it to measure the response and identify resonances or driving frequencies. So they applied a force with a voice coil actuator. The generated force was consisted of random vibrational waves between 100 hertz and 10,000 hertz, which was their operating frequency. And the response of the sandwich structure was measured with a Polytech laser. And essentially what they did was they created frequency response function plots. So they took the velocity and divided it by the force in terms of, and plotted that against frequency to see where there was a lot of movement and resonances. So for those who are not familiar with a FRF, spikes are attributed to the resonances and signify where a large amount of energy and movement is expected. They did this test at multiple temperatures, and what they noticed was at 80 degrees Celsius, which was determined to be their optimum temperature, they pretty much got a straight line in the FRF, suggesting that there is little to no movement here, further supporting that their model was correct in determining the right operating temperature for their material. if we look here, we can see a lot of spikes at 20, 50, and a little bit less at 130, but at 80 degrees Celsius there, it's pretty much a straight line there. Now, this was a lot of work, and I'm this is pretty unreasonable for a lot of groups to do, but I think this just shows how, like, understanding what your frequency is or what your need is, you can really tailor DMA to fit your need. I think of George E.P. Box's quote, essentially all models are wrong, but some are useful. So um, whether it's the most extensive model or a very simple model, depending on your application, you can, depending on your application, you can tailor it for your need. And just as some closing remarks for this presentation, DMA can help measure and predict the damping performance of viscoelastic materials. Metrovib's high-frequency DMA capabilities allow you to measure rheologically complex samples like our example in case study 1 did. And just to show kind of the frequency spectrum of NVH and the DMA measuring capabilities, I just added this plot here where we can see that traditional DMAs typically measure up to 200 hertz, but with the Metrovib Plus series, you can measure up to 1,000 hertz, and the Metrovib VHF 104, you can measure between 100 and 10,000 hertz, which covers a lot more ground with the vibrations that are typically studied in with NVH. But I also did want to highlight that you can model high frequency performance with other DMAs or Metrovib DMA as well through WLF, but just to take the proper precautions and to be safe and to design your experiments with the expectation of these limitations. So that concludes our presentation today. I just want to finish off with addressing a couple other little housekeeping issues. So if you found this interesting, or if you're interested in thermal conductivity or one of the other products we offer here at C-Therm, we have tons of webinars. We have a great extensive tech library where you can look up keywords to find more information about application related to you. For upcoming events, we'll be at Polymer Testing World Expo in Europe in June, and we'll also be down in Michigan for the Adhesives and Bonding Expo, in Novi, Michigan. And another upcoming webinar we got at the end of the month is just kind of more of an introduction to how to measure thermal conductivity, applications and method overview. So this will be if you're new to thermal conductivity or need a refresher, this will be a great webinar for you. You can follow us on LinkedIn, where you can stay tuned for more upcoming webinars, blog posts, or events that we'll be at. And if any of this was interesting to you, you can book a demo with us. We can set up some DMA tests to run on your samples. We can run them here or at the Metrovib facility. You can also request a quote. We can set up a call to kind of talk a little bit more about your experiments and see if there's a good fit for what you guys are doing. And yeah, I guess we'll go on to questions here.